Good morning, students. I am Suneetha, Assistant Professor of Chemistry from KGC Hanamkonda. Today we are going to discuss about group 14 elements. There our subtopic is silicones. Silicones. What are silicones? Let us see. Silicones are a group of natural organosilicon polymers based on rings, chains, or network of alternating silicon and oxygen atoms having the general formula SiO 4 minus N by 2. This is the general formula of silicones, where N is between 0 and 3, and here M is also there. That is the overall unit of this particular silicone, that M is 2 or more than 2. So silicones are a group of natural organosilicon polymers. Organosilicon polymers in the sense organic moiety is present and silicon is also present here. Organosilicon polymers based on rings, and they will be having the structures will having either rings or chains or network solids, network silicones. So these are all different structures these silicones are having. We will discuss about the classification of silicones now. Now, the silicones are fairly expensive, but they have many desirable properties. They were originally developed as electrical insulators because they are more stable to heat than organic uh, polymers. And if they do break down, they do not produce conducting materials as carbon does, that is, organic polymers does. So they are resistant to heat, oxidation, and most chemicals. So they do not undergo oxidation so easily, and more towards more chemicals they are resistant, and they are resistant to heat also. And they are strongly water repellents, and they are good electrical insulators, and they have non-stick properties and anti-foaming properties. Because of all these uses or applications, the silicones, they are very important, and their strength and inertness are related to two factors. What are they? First one is there's a subtle silica-like skeleton of SiO. And this SiO bond energy is very high, that is around 502 kilojoules per mole. This is very high energy, that is, this bond is very strong. And this SiC bond is, see here, SiC bond is also very strong. And SiO bond is also strong, and SiC bond is also strong. And their water repellency arises because of silicon chain is surrounded by organic side groups. Due to the presence of organic groups, they are water repellents in this silicones, and they look like and alone from the outside. So, and the silicones, they may be liquids or oils or greases, and they are also rubbers or elastomers and resins. Now, how these silicones are classified? Let us see. Silicones are classified into the three types. One is straight chain silicone, second one cyclic silicones, third one is cross-linked silicones. So silicones are classified into three types: straight chain, cyclic, and cross-linked or network silicones. Now let's see the preparations of silicones, how the silicones are prepared. First preparation. Generally, the silicones are prepared from the intermediates. So, what are the intermediates? The intermediates are alkyl chlorosilanes or aryl chlorosilanes. So, first of all, we should prepare these intermediates. From these intermediates, silicones can be obtained. So, first one is direct silicone process. Direct silicon process. So, in direct silicon process, chlorinated hydrocarbons react with silicon in presence of metal catalyst. Chlorinated hydrocarbons, that is chlorohydrocarbons, they react with silicon in presence of a metal catalyst like a copper at about 300 degrees centigrade. And here, let us see the reaction. This is silicon. This is chlorohydrocarbon. That is a specific example is methyl chloride we have considered. And this is the metal catalyst. Copper metal catalyst is used and heated to 300 degrees centigrade. Then we got this particular compound, that is CH3SiCl3. Okay, CH3SiCl3. This is Mm, generally SiCl4 is silicon tetrachloride. Here methyl silicon tetrachloride. This is chlorosilane. This is chlorosilane. Okay. And similarly, if only one chlorine atom here, in this case, let us see this methyl chloride, it reacts with silicon in presence of metal catalyst at about 300 degrees centigrade to form this particular compound, that is CH3SiCl3. Okay, CH3SiCl3, this is the compound obtained here. And apart from this, we also get this one. This is dimethylsilane. This is methylsilane. This is dimethylsilane. And other products, other compounds like this, we will also get other compounds having more number of methyl groups. So a mixture of silanes chlorinated, and this is chlorosilanes are obtained in this reaction. So this is the intermediate preparation, direct method. Next one is use of Grignard reagent to prepare the chlorosilanes. Yes, to prepare this is chlorosilanes, alkyl chlorosilanes. Okay, alkyl chlorosilanes. This is the second method, that is use of Grignard reagent. So silicon tetrachloride, that is SiCl4, it may be converted readily into alkyl or aryl derivatives by this method. So let us see how they are obtained. So SiCl4, it is when treated with the methyl magnesium chloride, that is one of the Grignard's reagents. And then what happens? We get this alkyl chlorosilane. Alkyl chlorosilane is the product obtained in this reaction. So this is methyl CH3SiCl3. So from this SiCl4, one chlorine atom is replaced by methyl group. You can see here. The CH3SiCl3, other product is MgCl2. And here, and this is CH3SiCl3. It again combines with one more mole of this particular Grignard's reagent. Then what happens? Another chlorine atom of this particular compound is replaced by and one more methyl group. Then we will get this dialkyl chlorosilane. The alkyl chlorosilane is obtained. And in next step, this one, it combines with one more mole of this methyl magnesium chloride, that is Grignard's reagent. Then what happens? Another chlorine atom is replaced by methyl group. Thus we get trialkyl, the trimethyl chlorosilane is the product obtained in this method. Okay. So this is the second method. With the help of Grignard's reagents, we can prepare alkyl chlorosilanes, which is the intermediate for the preparation of silicones. Next method is aromatic silylation. So, in the previous methods, we prepared only alkyl chlorosilanes. Here, we can also prepare aromatic silylation. That is, aromatic chlorosilanes can also be obtained. So, in this method, we are going to prepare aromatic chlorosilanes. So, a useful range of intermediates like aryl silicon halides. Aryl silicon halides. If it is chlorine, aryl silicon chloride may be prepared by the reaction of benzene and other aromatic hydrocarbons at about 230 to 300 degrees centigrade with the compounds of silicon, compounds containing silicon and hydrogen bonds. Okay, so catalysts like BF3, BCl3, AlCl3, the Lewis acids are used in this reaction. Now let's consider this one. This is benzene, an aromatic compound. When it is treated with this particular compound, this is trichlorosilane. When it is treated with this trichlorosilane, what happens? From one hydrogen atom from this is replaced by this one. From benzene is replaced by this SiCl3 group. Then we get this particular compound. This is aryl, that is phenyl chlorosilane. Okay, this is the compound obtained. So the product is also accompanied by small amounts of that is diphenyl compound, triphenyl compound like this C6H5 taken twice, SiCl2. Okay, or another compound with this hydrogen is retained, and one H from this and Cl from this is lost. So you can see this compound is obtained. So this is uh, from this compound, one chlorine is replaced, and this phenyl group is attached. Then we will get this particular compound. This is aryl chlorosilane. Okay, monoaryl, idemo diaryl, diphenyl, let me say in particular. So this is aromatic silylation. These are the intermediates produced in this reaction and which can also be used for the preparation of silicones. Now next one is another preparation. A wide variety of olefins, that is alkenes and acetylenes, are able to react under suitable conditions with halosilanes or organosilanes containing one or more SiH bonds in the molecule. So let us see the compounds containing SiH bonds. They react with olefins, that is alkenes or acetylenes, to form halosilanes or organosilanes. Now let's see. This is halosilane combines with alkene. This is C. Halosilane combines with an alkene to form this particular intermediate, which is used for the synthesis of silicones. Used for the synthesis of silicones. So these olefins or acetylenes, they react with halosilanes or organosilanes, which contain the such type of SiH bonds to form the required intermediates used for the synthesis of silanes. Now let's consider this example. This is trichlorosilane combines with an alkene to form this particular intermediate. And next example here, methyl trichlorosilane combines with another alkene, and heating to about 500 degrees centigrade, we get an intermediate compound which is used for the synthesis of silicones. Now all these reactions, they occur without a catalyst, but various initiators are used to secure a lower reaction mixture, which may be important if the desired products are thermally unstable. So they include organic peroxide. So here organic peroxides are used as initiators in this reaction. Next one, hydrolysis. Here in the case of hydrolysis of dialkyl dichlorosilanes, the reaction, it proceeds in this manner. Dialkyl dichlorosilane. So dialkyl, two alkyl groups, dichloro, two chlorine atoms are present. Dialkyl dichlorosilane. This is the example for this dialkyl dichlorosilane, which undergoes hydrolysis. Then what happens? These two chlorine atoms are replaced by OH groups. You can see here R and R intact silicon, and here one chlorine is replaced by OH group, and another chlorine atom is also replaced by OH group. Okay, so this is the hydrolysis reaction plus 2HCl, right? Now when this particular compound, this is hydroxy dialkyl dihydroxysilane. These molecules, they combine, then we will get silicones. So the compound which contain Si bonds, which are called silicones. So here we got a silicone. Next, in this molecule, the OH group, active OH group is left at each end here. OH group is present. This side also OH, both the ends, active OH group is present. Because of this reason, what happens here? The polymerization reaction continues and the length of the chain continues to increase this side. One more molecule of such type of dialkyl dihydroxy silane, if it combines with this particular one, the length of the chain increases and polymerization reaction, it continues. Okay, and at the length of the chain also continues increasing, in continues to increase, giving a long chain product like this. Okay, this reaction, it continues because at both the ends the active OH group is present. Okay, next one, preparation of cyclic silicones. Preparation of cyclic silicones. Now, cyclic are ring silicones. They are formed when water is eliminated from the terminal OH groups of the linear silicones. See here, this is the linear silicone. From this linear silicone, from the terminal OH groups, see, this is the silicon, linear silicon. This is terminal OH, this is terminal OH. From this terminal OH groups, if water molecule is removed, then we will get a silicon like this. This is cyclic silicon. So cyclic silicon is obtained when water molecule is eliminated from the terminal OH groups of the linear silicon. So from this is the linear silicon, this is the terminal OH group, this is the terminal OH group of this particular end and terminal OH group of this particular end. And from this, when water molecule H2O is lost, we will get cyclic silicon. Next one, preparation of cross-linked cross-linked silicones. A complex cross-linked polymer is obtained by the hydrolysis of monoalkyl trichlorosilane. Monoalkyl trichlorosilane, that is one R group and 3 chlorine atoms are present. One silicon. Monoalkyl trichlorosilane, that is RSiCl3. Monoalkyl trichlorosilane, RSiCl3. When it is subjected to hydrolysis, we get cross-linked polymer, silicone. RSiCl3, monoalkyl trichlorosilane, subjected to hydrolysis. Then what happens? These 3 chlorine atoms are replaced by OH groups. We can see here RSiOH taken thrice plus HCl. And when this intermediate, it undergoes the polymerization, then what happens? The terminal OH groups, from this terminal OH groups, water molecule is lost and we will get a cross-linked polymer here. This is a linear polymer and these linear polymers, they combine to form cross-linked polymer. So like this, see, one linear polymer, another linear polymer. They combine to form, here also loss of water molecule takes place and we will get a cross-linked polymer, a network solid like this. So silicon rubber is prepared from the gum of cross-linking of chains like this. This is a chain polymer. This is a chain polymer. And then what happens? These two chains, they combine by the loss of water to give a network solid or cross-linking chains. So bases, they catalyze such type of reactions. And here the base in the sense such as alkali metal hydroxide, that is sodium hydroxide, potassium hydroxide, etc. are used here. And they are here they are used for the cleaving silicon oxygen bonds to yield a linear species which then acts as a chain propagation center. Okay, so when this silicon oxygen bond, when this bond or this bond is broken with the help of alkali metal hydroxides, then what happens? The reverse, we will get a chain, linear species, linear species or linear chain is obtained. Now let us say this. The higher the concentration of the catalyst, the lower will be that average chain length. And the concentration of this particular alkali metal hydroxide, the concentration is high, then what happens? Lower will be the average chain length. So we will get the shorter polymer. The length of the polymer chain will be less when the concentration of this particular alkali is more. And the length of the chain can be reduced by adding end capping reagent, which is most commonly hexamethyl disiloxane. This is end capping reagent. What it will do? It is used to reduce the length chain length of the uh, polymer, linear polymer, by using hexamethyl disiloxane. Hexamethyl disiloxane is used to cap one end so that the length of the chain can be reduced. Here, this one, KOH, if it is used, this bond is broken. This bond is broken. The, any one bond, so that we will get a linear polymer. When this bond is broken, we will get a linear polymer like this. When this bond is broken, we will get a linear polymer like this. Okay. So this end will be having an active OH group. If this bond is broken, this end will be having active OH group. Okay. So like that, we will get a linear polymer, and the length of the linear polymer chain can be reduced with the help of a end capping, by adding an end capping reagent, that is hexamethyl disiloxane. This one, hexamethyl disiloxane. Okay, methyl group, here three methyl groups, here three methyl groups, and SiOSi. So this is hexamethyl disiloxane. This is used to reduce the chain length. Okay, next. Properties of silicones, and these silicones, they have high thermal stability, and in the absence of air they will withstand temperatures up to 250 to 300 degrees centigrade. So oxidation of organic groups in the structure first occurs at about 2000 to 2500 degrees centigrade and leads to cross linking. So this is the first property regarding thermal stability of silicones. And next one, let's see this. These are silicones are water repellent because of organic side groups, and materials such as paper, wool, textiles, wood, porcelain can be made waterproof with a coating of thin film of silicones. So all these compounds, that is paper, wool, textiles, wood, etc., porcelain, this can be made waterproof with the help of silicones, because silicones are water repellent. Okay. And why they are water repellent? Because of the presence of organic side groups. And this is achieved by simply exposing them for second or two, 1 or 2 seconds, to vapors of trimethyl chlorosilane. When their surface becomes coated with a thin layer of this group, which repels water like hydrocarbon, like this group, when it is present on these particular compounds, it repels water like a hydrocarbon. So because of this property, they are used in car polishes and in anti-stick formulations, and for here example, artificial heart valves and artificial that is heart bypass pumps are fabricated from silicone rubber, because they are water repellent. Next one, they are also unaffected by the majority of mild chemical reagents such as weak acids and alkalis or salt solutions. So they are really, very much stable towards weak acids, alkalis, that is bases, and salt solutions. And many of the low molecular weight silicones, they dissolve in solvents such as benzene or ether or carbon tetrachloride. This is about the solubility of these silicones with low molecular weight. They dissolve in solvents such as benzene, ether, and carbon tetrachloride. And all this, they have good electrical insulating properties. Silicones have good electrical insulating properties, and if they break down, they do not produce conducting materials like carbon. So here the silicones, when they break down, they do not produce conducting materials, whereas hydrocarbons, they produce conducting materials on breaking down. Next, one of the outstanding property of the silicones is their small variations in viscosity. It changes in temperature. When there is a change in temperature, what happens? Their viscosity will be changed, and therefore they are used as lubricants at both high and low temperatures. Example is given here in greases and oils for engines and motor that operate in regions of extreme temperatures. So here these silicones, they are used as lubricants because of their uh, difference in the viscosity with the changes in the temperatures. Next, let us see the structures of silicones. This is a straight chain silicon. So any compound which has OSIO bond is called a silicon viscid. So these are the alkyl groups, that is here a specific example methyl groups we have given. These are straight chain silicons here. Example is given, that is polydimethyl siloxane. This one. Okay. Next, cyclic silicones examples. This one. Me2SiO taken thrice. Me2SiO. This is one part. Me2SiO second part. Me2SiO third part. So Me2SiO taken thrice. This is cyclic compound which is trimer of this particular monomer. And this is another one. Me2SiO taken four. Such type of groups, four are present here. So Me2SiO dimethyl siloxane. One, two, this is 3 and this is 4. So this is a tetramer of this particular monomer, that is dimethyl siloxane. This is cross-linked silicon. We can see the cross-linking. Okay. So this is one example for cross-linked silicon. Now let's see what are the different uses of silicons. The uses of silicons are divided based on their physical properties. First one is silicone fluids. So these silicones, they are used as silicone fluids as they have low temperature coefficient of viscosity, which makes them valuable as hydraulic fluids. So their good electrical insulating properties and high thermal stability also make them to use as a dielectric fluids. So these are used as fluids, silicone fluids, because of their uh, electrical insulating property, and they can withstand to high temperatures. That is, they are having high thermal stability. Next one, silicone rubbers. So these are especially valuable because they retain their elasticity at lower temperatures than other rubbers, and are resistant to oils. As they are resistant to oils and they can retain their elasticity at low temperatures, these silicone rubbers are very, very important. And silicone rubbers withstand 400 degrees centigrade for 100 hours and 540 degrees centigrade for 90 hours. So because of this, their resistance to heat is much better than many of the organic rubbers. And because of their property to withstand heat, they are used in sealing joint and seams of jet aircraft, or insulating electrical parts such as transistors which cannot be heated. So in all this, uh, we find the use of silicones. Next one, silicone greases. Silicone greases vary in properties depending on the type of the fluid and thickener used. So these greases, they vary in the properties of the fluids and thickeners used in the greases, they will be having different properties, and they have wide service temperature range, that is about 100 to 450 degrees centigrade. So greases prepared from medium phenyl oil and lithium soap are used for ball bearings operating at high speeds and high temperatures. So the ball bearings which are operating at high speeds and high temperatures, the silicone greases, they find applications. So which are prepared from medium phenyl oil and lithium soap, which are used in these ball bearings. These ball bearings which operate at about high temperature, high speeds and high temperatures. Next one is silicone resins. The silicone resins are of many types: coating resins, laminating resins, water repellent resins, molding resins, and electrical resins. So these are the different types of silicone resins, and these are characterized by heat stability, water repellency, good electrical conductivity, chemical inertness, and weather resistance. So they have many special properties like heat stability, water repellency, they repel water, and good electrical conductivity they have, chemical inertness, they are chemically very much inert, and they are weather resistant. And to develop the other best properties, baking or heat treatments is given to them. Okay. This can be withstand high temperatures as high as 250 degrees centigrade, and coating made up to of silicone resins plus organic resins and aluminum can withstand temperatures up to 500 degrees centigrade and above. So, when the silicone resins are coated with this aluminum and organic resins, then what happens? Their heat resistance temperature is about 500 degrees centigrade and more also. So, release resins are backed on metal surface to prevent materials from sticking to this surface. Now let's discuss a few questions related to silicones. First one, what are the crystalline allotropes of carbon? That is, these are the all the questions which are related to 14 group elements. Not only silicones, but all the 14 group elements. So, what are the crystalline allotropes of carbon? That is, carbon, it has three crystalline allotropes. We have already discussed in the previous session that they are diamond, graphite, and fullerenes. And write the general formula of silicones. General formula of silicones in the first part of the introduction of silicones, we have discussed about the uh, silicones formula. Now let me show this silicones formula. We have discussed this one. RnSiO 4 minus N by 2 to the power M. Okay. This is entire group taken M. Okay, so where N is between 0 and 3, we said that is these are the alkyl groups or aryl groups, and M, and that is M stands for the number of these groups. Okay, so M is 2 or more than 2. So this is about that is these are the monomer parts which are present in that particular silicone. So number of monomers is given by this particular M. Okay, so M is always either equal to 2 or greater than 2, where this N or this N is equal to 0 to 3. So this is the general formula of silicones. Now let us see next question. So this one, general formula of silicones. Give examples for methanides. So what are methanides? We said methanides are the compounds which produce methane on hydrolysis. Methanides are the carbides which produce methane on hydrolysis. So calcium carbide is a methanide. Aluminum carbide is a methanide. Beryllium carbide is a methanide, whereas calcium carbide is acetylide. Next, what is the hybridization of carbon in CO2? about to undergo CSP hybridization. So mention the uses of silicone resins. Just now we have discussed the uses of silicone resins. Next, what are carbides? How they are classified? Carbides, they have many types of carbides we have discussed. Ionic carbides are in ionic carbides, covalent carbides, metallic carbides. Like this, we have number of carbides discussed in the previous video. Now discuss the synthesis and structure of carbides. So how carbides are prepared and what are their structures, that also we have discussed. And what happens when CaC2 reacts with water with equation. CaC2, when it reacts with water, that is hydrolysis reaction of CaC2. CaC2 is acetylide, and this, when undergoes hydrolysis, it forms calcium hydroxide, um, liberating acetylene gas C2H2. CaC2 plus 2H2 gives rise to calcium hydroxide plus C2H2, that is acetylene. Write the industrial applications of carbides. Carbides, they find a number of applications. Next, write a brief note on interstitial carbides. So here we should write about the interstitial carbides, how many types are there and how they are prepared, what are their uses, we should write. Next one, explain the reactivity of ionic and covalent carbides. So here we should discuss the reactivity of ionic carbides as well as covalent carbides. Comparative study. Define silicones. Write the preparations of silicones by direct silicone process. So direct silicone process, just now we have discussed how it is produced. So in direct silicone process, chlorinated hydrocarbons, they react with silicon in presence of metal catalysts like copper at about 300 degrees centigrade. So then we get the silicones and explain into preparation methods of silicones. The first one, this one we can write direct silicone method, and next one use of Grignard's reagents. So silicon tetrachloride when treated with the Grignard's reagent, then also we get the intermediates, that is alkyl chlorosilane. From that we can get the silicones. Now write a note on properties of silicones. Silicones properties. Silicones, they have high thermal stability. Next, they withstand high temperatures up to 250 to 300 degrees centigrade, and they undergo oxidation of organic groups at about 2000 to 2500 degrees centigrade, and they lead to cross-linking with it, and they have water repellent. They are water repellents due to the presence of organic groups as side groups, and they are unaffected by majority of mild chemical reagents with it, and they are less reactive towards weak acids and alkalis and salt solutions, and they dissolve in solvents like benzene, ether, carbon tetrachloride, etc. We said this is about the solubility, and they have good electrical insulating properties. That is another property, and if they break down, they do not produce conducting materials like carbon. So these are all the different properties of silicones. Next one, next question is about discuss the what is this classification of silicones. So how silicones are classified? Classification of silicones is silicones are classified into three major classes. One is straight chain silicone, second one cyclic silicones, and third one is cross-linked silicones. Next, mention the uses of silicones. How these silicones are used, what is their importance. Silicones, they find many applications or many uses with it. One is used as silicone fluids, next one silicone rubbers, next silicone greases, and silicone resins. These are all different major uses of silicones. Next, what are the products formed when dichlorodimethyl is hydrolyzed? Dichlorodimethyl is R2SiCl2. When it is subjected to hydrolysis, we get what do we get? Dialkyl dihydroxysilane. Okay, that is two chlorine atoms get converted to two OH groups. Chlorine atoms are replaced by OH groups. That's all. So we get R2SiOH taken twice as the product. Now let's see the few multiple choice questions in this, which is which compound acts as a lubricant. So, in the carbon compounds, allotropes of carbon, lubricant. Graphite is slippery and soft, therefore it is used. It acts as a lubricant. That is, this is the answer. Graphite. Next, reaction of SiO4 with HF. What is this? SiO4. Okay, silicon tetroxide. When it is treated with what do we say? HF is hydrofluoric acid. Then what is the product obtained? So in this reaction, that is SiO4, when it combines with HF, that is hydrofluoric acid, the product obtained is H2SiF6. This is the product obtained. And next question, let's see. What is that? Which is the interstitial carbide? Interstitial or metallic carbides. The example for interstitial or metallic carbide. So here we have first option tungsten carbide, this is magnesium carbide, this is beryllium carbide, and last one is silicon carbide. Silicon carbide. So the metallic or interstitial carbide, and generally we know metallic carbides are formed by transition metals. Therefore, this must be the answer. So A. This one is the answer for this. This is tungsten carbide. Next, silicones are classified into dash types. So, silicones are classified into three types: research straight chain silicones, cyclic silicones, and cross-linked silicones. The answer is this one. They are classified into three types. Next, hybridization of carbon in carbon monoxide. Hybridization of carbon in carbon monoxide and carbon dioxide is sp. This is the answer. Okay. Now let us see next question. This is the fill in the blanks. The tendency of an element to form long chains containing identical atoms is known as, this is the special property of carbon, that is catenation. So answer is catenation. And next one is bond length in carbon monoxide. Carbon monoxide, the bond length is 113 picometers. 113 pm. Okay. Next one is calcium carbide. When it undergoes hydrolysis, the product obtained calcium hydroxide plus acetylene. This is acetylide. Therefore, acetylene is the answer. C2H2. And next one, what is this? SiF4. When it undergoes hydrolysis, the products obtained. SiF4 on hydrolysis, it produces silicon oxide and HF. So HF and SiO2 are the products. So 8 HF and 2 SiO2. Answer. Next one is beryllium carbide. Beryllium carbide is a methanide. So beryllium carbide, when it undergoes hydrolysis, the product obtained is, one is beryllium hydroxide, the other one is methane. So BeOH taken twice plus methane CH4 are the products obtained in this reaction. So these are the different types of questions we come across from this 14 group elements, that is 4th group elements or 14 group elements, that is carbon family. So in this we discussed in 14 group elements the chemistry of carbon and silicon. Chemistry of carbon and silicon we discussed, and we have already also discussed a number of different types of questions, short answer and long answer questions. we come across from this lesson. Okay, so these are the questions we come across. These are the multiple choice questions in the different entrance examinations you will face. Thank you. With this, we will stop this today's video lesson, and I'll continue with another topic in the next session. So, with this, I'll conclude. Thank you once again.